Hi, and welcome to the Hamburg office of ParityQC. My name is Simanraj, and I'm a quantum optimization engineer.
Hi, my name is Florian. I'm a quantum hardware physicist here at ParityQC. I have a background in spin qubits, which is what we're going to talk about today. In the past decades, humanity has become very good at one thing, making transistors from silicon. Since you clicked on this video, thousands of trillions of transistors are fabricated, each of them just a few nanometers in size, so that you can fit billions of those onto a centimeter-sized chip. You can find these chips in cars and washing machines and your smartphone. They make the internet, video games and AI possible in the first place.
However, for specific problems like optimization, which have applications in areas like logistics, material sciences and drug design, we have reasons to believe that a quantum computer will do a much better job than a classical one. But we need to make quantum computers scalable, and for that, we need to be able to put billions of qubits on small chips. For this, we seek inspiration from the semiconductor industry, which already has a proficiency in chip fabrication.
25 years ago, our scientists proposed that the spin of an electron, confined in a quantum dot, can be used as a qubit. These quantum dots are almost identical to transistors, and there were many amazing results in the last 2 years. Spin qubits indeed seem to be a promising candidate for quantum computing.
There is a caveat though. The interaction between spins is usually very short range. For example, on a chip, the spins can only talk to their neighboring spins. But to harness the full potential of a quantum computer, we also require long-range interconnectivity.
Researchers came up with a hack. It is possible to physically move the electron around on a chip and bring it where it is needed. Now, this is called spin shuttling. But spin shuttling is not perfect. The further a qubit needs to go, the more likely errors will occur. And this means that the range is still limited.
This is where the ParityQC architecture comes in. So in the ParityQC architecture, only nearest neighbor interactions are required for quantum computing. Some adaptable algorithms allow for simplified control and shorter circuit depth. And on top of that, the ParityQC architecture allows for error mitigation and some error corrections.
Now remember that spin qubits are very similar to transistors, and we know how to make many of those laid out in 2 dimensions. So if we combine the potential of spin qubits with the benefits of the ParityQC architecture, could this be a scalable quantum computing platform?
In a recent study with our partners at ARQUE Systems, we investigated the performance of a parity quantum optimization algorithm on 2 possible spin-qubit architectures. Both the architectures are constructed from simple unit cells, and they use shuttling over short distances.
First, we came up with shuttling sequences that are identical on every unit cell. Then we used a detailed noise model to estimate the errors. Based on these results, we identify the most important error sources, and we estimate the performance.
We can expect some advantage over a non-parity algorithm for the same problem on similar hardware. And the spin qubits need not fear comparison with other hardware platforms like the superconducting qubits. In fact, in some cases, it may even beat them.
We also looked into quantum error mitigation for improving the outcome. There, we showed that the spin qubits can reach a regime where error mitigation is useful, and that a clever decoding scheme allows to further suppress the errors after the computation.
For applications of quantum computing, it is important to relate the requirements of a quantum algorithm and also the capabilities of the existing hardware platforms. And now we know that spin qubits and ParityQC architecture have great synergy for quantum optimization.
This can provide some guidance for the development of future scalable quantum computers. It is only a starting point though. We have many exciting ideas to leverage quantum computing using key aspects of the hardware.